Okay, we're going to look at the details of how to use and interpret the Skew-T log P diagram. Critically important dealing with severe thunderstorms. You have to know how to manipulate these profiles. What do they mean? And so I'm going to go all the way back to the beginning. We're going to talk about, I don't know, how many people have actually used a Skew-T log P diagram? Okay, and if anyone hasn't, this is your chance to catch up, hopefully, with the rest. This is just the in-Sharp version. This should look pretty familiar to the Python version of Sharp, which anybody can run if they want to now. The idea here is I'm going to focus in on the thermodynamic diagram, and we're going to identify what the contours are on here. This is what constant temperature looks like on a Skew-T log P diagram. And they slope from the lower left to the upper right, and I've just highlighted it here. That's a dry adiabatic lapse rate, so this is the rate of cooling for unsaturated parcel ascent. So you can see that it crosses over almost a 90-degree angle to the isotherms, and that's where the skew comes from. This is where the name Skew-T. So we're trying to get a big difference between the dry adiabatic lapse rates and the temperature contours, which is a way to show buoyancy. So the Skew-T diagram is important for thunderstorms because it's designed to highlight things like buoyancy. So there's a big difference between the lifted parcel ascent and the background temperatures. Constant pressure, it's a logarithmic scale. They're just the horizontal lines, and you can see they're packed tighter at the bottom, and they spread out with height. And the atmosphere, I believe the pressure goes to about half of sea level. Is it about 500 millibars? So that's about half of the actual atmosphere is above and below that. And then constant mixing ratio. And you notice here the skew between the mixing ratio and the temperature lines. Mixing ratio actually crosses the isotherms. So that's important to know. Elevation or the pressure matters in terms of moisture. So a dew point temperature at Denver, the same dew point compared to here in Norman, doesn't mean the same thing on the diagram. Okay, so the features, again, it's the skewed temperature. We've got the logarithmic decrease in height, and that important one I point out is that the mixing ratios cross over, so again, elevation or the pressure matters, and that's why it's important to know the difference between the high plains, the low plains, the Gulf Coast, or you're sitting on top of a mountain. The moisture, it actually makes a difference. And then, of course, the one thing that we don't have on this plot is I don't show you the moist adiabats. So the pseudo-adiabats, which represent the rate of change when you have latent heating accounted for. So this is what it looks like if you were just lift a parcel dry adiabatically. That's the rate at which it would cool. So I just start with something that looks like a typical August heat wave around here near 40 C. It's 100 plus degrees Fahrenheit. If you lift it, by the time you get to 500 millibars, you get a temperature, minus 10 or 12 or something like that C. So the rate of change of temperature drops by almost 50 degrees C, just rising about 20,000 feet. Now, this is the moist adiabat. When you account for the latent heat release, if you start over there again, saturated parcel with 100 degrees roughly, which is pretty ridiculous. I don't think anybody's been in a dew point of 100 Fahrenheit, but if you do this, there's a tremendous amount of latent heat release. So notice the difference between those two parcel curves. One of them cools, dry adiabatic is almost 90-degree angle to the isotherms, whereas you look at it's closer to 45 degrees for the moist adiabat. The difference between those two, that's where buoyancy comes from, is the difference between these two lapse rates, which is the key when we look at, and I put it in there in blue, that area between those two, if you look at it like that sort of pie wedge, those are conditionally unstable lapse rates. That gives us the potential to have buoyancy if you have a saturated parcel ascending through a layer with lapse rates somewhere between dry adiabatic and moist adiabatic. So those are the lapse rates, roughly somewhere between 6.5 and 9.5 degrees C per kilometer is what we're looking for thunderstorm environments. All right, so the lifted parcel, we begin at the ground, and I'm going to illustrate this. We go up dry adiabatically. There's no latent heat release at this point until the level, or the lifted condensation level. That's our first guess at cloud base. This is basically how high do we have to lift it before the parcel's temperature cools to its dew point. And then, so what this looks like on the Skew-T, this is, if you look down here at the bottom, I've highlighted, we're starting from the surface, we go dry adiabatically up. Well, we need to find out where it saturates. Well, the mixing ratio, it's where that dry adiabatic lapse rate intersects with the mixing ratio. This little point right here, right there, X marks the spot. which it's already plotted on the diagram, and that's the level, lifting condensation level. So this is a first guess at cloud base, and in this case we're using the surface parcel. From there, we just calculate the rest of it. We're going to go from the LCL, which is the lifting condensation level, and it helps to know these terms, LCL, LFC, all this stuff, so that, because eventually I'm not going to spell it out every single time. It just takes too long. So we're looking for where does that lifted parcel end up being warmer than the background environment, and how much energy has to be expended to get it there, and that's the convective inhibition. And then from the level of free convection, we go all the way up to the next time way in the upper troposphere. Typically, that's the equilibrium level, where the temperatures are equalized again, and everything between there is what we would use to calculate buoyancy. So we'll just show you some of the common values. Again, this is just stuff you want to have in your toolbox. You want to understand this without having to stop and think about it because again, this is where the mechanics kill you. If you're having to think about, wait, what's that lapse rate? Wait, what does LCL mean? What does LFC mean? You get lost in all the details and you're not thinking about the forecast. So again, just these, if you're not familiar with them, I just suggest memorizing them and play with soundings a few times, and eventually it becomes easier to deal with. Okay. So let's show, the important thing is we'll show an example. We're going to lift a parcel and go through the whole calculation here. So we're starting at the surface. We found the lifting condensation level. That's the first part of unsaturated parcel ascent. Now we form clouds. So we're saturated. Now we're releasing latent heat. Now in this case, there's going to have to be something to lift this parcel here, because you notice in the environment, to get to this level of free convection, which is marked right here where it finally crosses over to where it's warmer than the environmental profile for good, there's a layer in here that's actually warmer. So that's where the convective inhibition calculation would come from. So we're going to have some sort of forcing for ascent to overcome this. The parcel one is not going to get to the level of free convection on its own, so that's why ascent is important. And again, you'd calculate the convective inhibition is sort of the integral of this little sort of triangular shaped area there, and then we continue up. And then eventually, CAPE is just the integral of all of this positive area between the lifted parcel trace and the environmental temperature. So we're just looking, and typically the way this is calculated is break this down into little teeny layers like 10 millibars thick, and you do a mean temperature difference between them. And if you've seen the formula for CAPE, it's just the environmental temperature and the difference between that and the lifted parcel temperature. And then you just integrate it. It just adds up to a whole bunch of little layers of buoyancy. Okay. Now you notice on there were differences in the lifted parcels, and so I was showing you the non-virtual parcel ascent. So just to make sure you're clear what we're talking about there, that's the brown line. So if we go down, that would be this one on the left, and if you look at any of the N-sharp sounding plots, and they show both parcel ascents. So point here is that there's an influence of moisture, and this gets back to the ideal gas law, and it's been shown that you should account for the moisture content because it influences density. So the idea here is where the temperatures are warmer and the dew points are larger or the mixing ratios are larger, the virtual temperature is actually higher than the actual temperature. So when we look at the soundings and look at this, the idea here is that that's the non-virtual. All of our calculations that you see on the SPC mesoanalysis page, they're using the virtual corrected parcel ascent. So that's the white line. And if you notice what these two do is that they start off, the biggest difference is down here where it's warm and moist. You notice the difference between the virtual temperature is actually that thin dashed red line. Again, it's not the real temperature. But if you're calculating convective inhibition and CAPE, you have to compare the lifted parcel to the dashed red line. You're not comparing it to the solid red line. But the point is the virtual temperature is not the actual one. So we plot the actual profiles, but we calculate based on the virtual temperature correction. So the inhibition here is just this little area right there between the dashed white curve and the dashed red. So there's a little bit of a cap on this sounding for the surface parcel. And then you notice they become the same lines as we move aloft. The reason for this is it's getting very cold. We've condensed out all the water, so the virtual temperature asymptotically approaches the actual temperature. There's no additional moisture content, no change in density, so eventually they become one and the same. Okay, so the point here is when we get into, we're talking about thunderstorms. Okay, you need to know the mechanics of lifting these parcels. Point here is what parcel? What do we mean by a parcel? There's a bunch of different ways to do this. In this case, this is an illustration of the surface-based parcel ascent, large buoyancy, which is also the most unstable parcel. And that's not too surprising since you've got the warmest temperatures and the highest mixing ratios are at the surface in this sounding. So that one should be straightforward. If you take a mean of the low levels, typically you also see us display something like the 100 millibar mean parcel or the ML K% calculation. It actually averages out over the lowest 100 millibars, shifts the parcel ascent to the left because now you're accounting for lower mixing ratios, lower temperatures aloft. And it tends to be a more realistic view of the parcel ascent because the surface is literally just a point, whereas if you've got these updraft plumes, it's some mix of air from multiple levels. So usually some sort of mean parcel is a little more realistic version. And there's been work looking at cumulus fields and how high the cloud bases are, and the 100 millibar mean parcel looks like a better estimate to use to calculate the lifting condensation level. And by extension, the buoyancy calculations are more realistic as well. Okay, now here's another different kind of profile where it's stable right at the surface. Because you notice here, this is a case of an actual inversion. The temperature literally increases with height. A lot of what people call inversions are really just isothermal layers, but that's a case. Temperature increases with height. There's very little buoyancy for the surface parcel. You see a little bit up here, it's relatively cool. There's this little sliver of buoyancy. The 100 millibar mean parcel, actually the buoyancy increases because what are we doing? We're actually reaching higher up, deeper into this warmer, moister layer atop the shallow cold layer. And then if you go to the most unstable parcel, in this case near 850 millibars, now there's relatively large buoyancy. So it depends on what you're trying to describe in the atmosphere, plays a big role in what sort of parcel you're going to use. In this case, using the surface parcel is not going to tell you much, but if you're looking for elevated thunderstorm development, the most unstable parcel gives you a completely different answer. Okay, now this is just like QG theory and everything else. We're making a bunch of assumptions. We're assuming that there's no mixing of air from the lifted parcel with the environment. That's what we call entrainment. That means that the actual updraft speeds, if you've ever done the calculation using CAPE alone, it's not going to be quite as fast because there's some mixing of air with the environment, and that will tend to reduce buoyancy. We're also, the pseudo-adiabatic part, we're assuming that the rain just magically disappears. As soon as condensation forms and you got precipitation, that it just disappears from the lifted parcel. Truth is, it doesn't go away so easily, and what that's going to do is reduce buoyancy. Again, you've got the mass of water that you're trying to drag along with the parcel. So these assumptions are going to be sort of a rosy best case scenario of how strong a thunderstorm updraft might be. So most of the rest of this is going to end up resulting in weaker updraft velocities than what you would get from pure parcel theory, except when we get to supercells and you talk about pressure perturbations, and we'll show how that can actually give you a stronger updraft than buoyancy alone. And again, this is a first guess at a really complicated process. QG theory is a first guess at synoptic meteorology. How does the entire atmosphere work? Of course it's not going to include everything, but the beauty of it is in its elegance. It's relatively simple and it tells quite a bit without just having someone throw up your hand and say, oh, I don't know 100% of the details, therefore I quit. It's not going to help you make a forecast. Okay. The other thing that we need to keep in mind is that, you've got uncertainty in the measurements. Are they good? What do they represent? This is where your conceptual models come in. You have to know, what am I looking at? If you just blindly use everything, I'm always going to use the most unstable parcel. Well, I told you, there are different ways to look at that. That's maybe not always the best thing to do. And again, if you can highlight problems in the soundings, and in one of the upcoming presentations, I'll show just a couple of examples of erroneous data in soundings that are pretty easy to pick out. Okay, so let's apply some more of this, look at some of the actual diurnal processes. We're going to start with simple vertical mixing. What does it look like on a sounding? When you heat up the ground during the afternoon, temperatures reach a maximum, what happens to the profile on the vertical? Okay, so we've got surface heating, the ground warms, that drives thermals. You get mixing upward from the surface, but there's also mixing downward from aloft. And you will normally, in a kind of quiescent regime, you'll see the dew points in the afternoon actually come down as the temperature's warm and the mixed layer deepens. If you have horizontal advection, then you can offset that. We'll show some examples here. So here's a sounding from Norman, and this is in August, typical, not terribly exciting summer regime. You notice the winds are relatively weak aloft. This is not a very baroclinic environment. So you would expect vertical heating and mixing, or the heating and vertical mixing, to be the primary contributing factor. So this is the 12Z sounding. 0Z, this is what happened. This is an illustration. If you look, it's this layer, this mixed layer form. That's from the heat transfer, conduction from the ground. You heat the air right above the surface. That drives thermals. And again, this air is mixing upward, and notice it's following a dry adiabat, essentially. So that's a sign that you've got a mixed layer. It's unsaturated, and it looks dry adiabatic. Now there's one thing missing on this sounding that I'll show you, I think, on the next one. You notice this looks like, if we go back, that looks like just a pure dry adiabatic layer. Point is, dry adiabatic is just neutral for ascent. It's just if you nudge the air up, it'll keep going up. If you nudge it down, it'll keep going down. But air's not just going to rise simply because there's a dry adiabatic lapse rate. This just means there's no resistance to vertical displacement. So we need something else. Now, and the key here is I'd say while you're thinking about this, think about what time is 0Z in Norman compared to the solar heating cycle. Is it after max heating or time of max heating before? Think about that for a minute. And let's go out west, which is another hint as to where it is in the heating and mixing cycle. This is Flagstaff, Arizona, so we're sitting up on the rim, higher elevation, very sharp inversion in the morning, this stable layer, but you could see very quickly heating and mixing is going to get through that afternoon. You notice the difference on this sounding is if we look right down here at the surface, we've got the same kind of mixed layer, but what's that little super steep lapse rate? That's the superadiabatic contact layer. That's what drives the thermals. If you've heard of autoconvection, you basically get the lapse rate so steep that you do induce overturning, and it actually drives the vertical motion itself. So we need that superadiabatic lapse rate at the ground. It's just Flagstaff, this is still mid to late afternoon for their 0Z sounding, whereas Norman, it's past peak heating. The temperature's already past its maximum, and we're no longer adding heat and driving mixing. You're just, on the Norman sounding, you saw the net result of the mixing. This one is actively mixing as we speak. So the mix layer could even get a little bit deeper on this sounding if you were to launch one maybe an hour later. Okay, so what happens when we start bringing in some of the large scale forcing for ascent? And what does it do when we have moisture involved? Well, if there's large scale ascent, you should see the moist layer deepen with time from below, and if you can get advection to offset that, you won't see the moisture decrease at the surface. So I'm going to show you a series of soundings, observed soundings, that illustrate what does large-scale ascent look like when we do this. So we start with this sounding from Little Rock. We've got a deep moist layer, and I've highlighted where the ascent is occurring. This is 6 hours later, so this is a morning sounding, an 18Z sounding. You notice it's roughly following a moist adiabat. There's loosely saturated ascent. And if you remember from some of the QG stuff, the displacements are not going to be huge. I mean, we're talking about 1 or 2 kilometers over 6 hours is the most you normally see due to QG processes. So there's something going on in the background in this case, and it continues all the way through 0Z. So what we've done is we've deepened the moist layer, and from below we removed that convective inhibition layer. So that cap that was sitting on the sounding in the morning, this is what it looks like when ascent on the large scale acts on the profiles. So there's ascent in that 850 to 700 millibar layer. So what has happened going back to the beginning? Buoyancy's increased, convective inhibition's decreased. Oh, and by the way, vertical shear has dramatically increased in the profiles. So this is a cyclogenesis, strong, large-scale synoptic wave. This is the Super Tuesday tornado outbreak from 2008, if anyone's familiar with it. This sounding wasn't too far in time and space from 120-mile track EF4 in Arkansas. So this is a case where the background pattern is setting the stage for severe thunderstorm development. It's changing the thermal profiles, it's changing the buoyancy, it's changing the vertical shear. And so again, that's what it would look like in real soundings. Now here's one, same kind of thing. You see over these are 6 hours apart. You've removed that layer of convective inhibition. You've kept the moist layer, because in this case, you notice the moisture is not really decreasing during the afternoon, even though there is mixing down low, because we're also advecting in higher moisture content from somewhere upstream. So this is pretty typical, and this is the same day. So this is Shreveport, which is a couple hundred miles south-southwest of Little Rock. So this is another example. If it's large scale, you're going to see this over multiple sounding sites, this sort of response.